And then we are going to take a look at the CUDA memory model, which is the main focus of this class. So we're going to take a look at what are the different kinds of memory in CUDA. And we are also going to take a look at how you can synchronize between threads on a GPU, which is very important because if you don't synchronize correctly, you will end up getting the wrong results on a parallel program. So first of all, if you have any questions regarding the lab, so just let us know. And then also another thing is that as you witnessed in the previous lab, so there's always like a pre-written code, which is sort of like a template. And then you need to first understand what that code does and then work on the problem. So in your first lab, you had received the vector add code. And then you worked during the lab, you worked on modifying it to ensure the correct execution. So the other labs will also follow a similar template, and you'll be doing these experiments during the lab. So let's get started. So we'll talk about the CUDA memory model today. So this is a brief overview of how the memory model looks on the left-hand side. So remember we talked about what is a grid and what is a block in the previous class. So inside the block, there's the concept, or there are different scopes of memory that are visible to threads that are part of the same block. So the first is each thread has access to its registers, which is private to it. And then there's a concept of local memory, which is based on the cache. And we'll take a look at what local memory exactly is. And then there's something called shared memory, which belongs to the scope of a block. So all the threads within a block can use this shared memory. And we'll take a look at later on why shared memory is important and how you can leverage it for improving performance. And there are other types of memories as well, which is global memory, constant memory, and texture memory. So one thing to note is that do not take a look at this diagram as a hierarchical way, especially the last three. It's not like one is on top of the other. It's just presented that way. So just keep that in mind. It's not like there are three DRAM memories, which is one is global memory, one is constant, and one is texture. So just something to be aware of. And on the right hand side, we have the GPU architecture, which we have previously looked at. So these are the different SMX, the green ones. And then each SM has a private L1 cache and a shared L2 cache. So first of all, let's go over the basic question as to why as a programmer you need to understand the memory model. And the reason is that understanding the memory model itself has a huge impact on performance when writing GPU programs. So understanding what kind of accesses your application is making is a key to enabling higher performance. So memory patterns allow you to control these effects, and it will help you to also maximize the resource usage by taking efficient care of the load store units. And to do this, we introduce the concept of data locality. So first of all, in traditionally, generally, I'd say that most applications do not have random accesses. They have like a sort of pattern of accesses. For example, you you access one element, then you access the next element, and then the next element beyond that, and so on. So it won't, very few applications, and there are some applications, but some applications will have some sort of random in their accesses. But traditionally speaking, most applications which are suited for parallelization usually have a very good ordering of memory access. And that's because random accesses are very hard to improve because it's totally random. So there's not much you can do about it. So having locality in your data helps performance. And there are two types of data locality that memory architectures make use of, or any sort of memory concepts in an architecture-based domain. So first is temporal locality. So that is, if you use a data, then you're going to use it again in the near future. For example, if you use something at time t, you might again be referencing at time t plus 5. So that's called temporal locality. Then the second is spatial locality. So the concept is that useful data tends to be followed by more useful data. For example, if you have an array and you access x of 0, then there's a chance that you're going to access x of 1, x of 2, and so on. So this is spatial locality because in memory, these x of 0, x of 1 would be laid out consecutively to each other. So useful data tends to be followed by more useful data. And that's what, even in general concepts, the caches would take advantage of these two types of locality, temporal and spatial locality. So we know, like for those of you who know the CPU architecture, you know what CPU caches do, and basically they store frequently accessed data. So the idea is that you could store this frequently accessed data in a small portion of your cache memory, so that the processor can access it faster. And then whenever something new comes in, you decide whether you want to keep that data and what data you want to remove. And that would depend upon the replacement policy of the cache. But the idea is, again, to make some of the frequently used data accesses fast. So GPUs also have caches, and they exploit locality at different levels of the memory model. But in traditionally, like, GPU caches are smaller than CPU, and you already know why that is, right? So the GPU is more latency tolerant than a CPU. A CPU architecture needs a larger cache, because if a thread has a cache miss, then it takes a lot of time to load from memory. On the other hand, in GPU, because on the same core, you have so many different threads that are running concurrently. So you can basically, even if some of the threads suffer a cache miss, you can bring in the next set of threads and have them execute. But at the same time, you don't want your cache hit rate to be 0, because that would have a negative impact on performance. Because if all the threads suffer cache misses and they all go to global memory or the DRAM memory, then it will take a long time to resolve these misses from memory. And as a result, it's still good to have a good high cache locality or a better cache hit rate than 0. So the different types of memory available on the GPU, the first is registers. On the right hand side, these are here. And then there's shared memory, local memory, global, constant, and texture memory. So these are, we'll discuss each of these memory and what they mean and how they are used in a typical GPU program. So first, let us talk about what is global memory. So the basic idea is that it resides in the device memory. So by device memory, I mean that the GPU has its own DRAM, which is type like GDDR5 or something like that. So it would reside in, so that's the portion of memory that's called global memory. And the scope of this memory is across the device, right? And it is the largest memory on the GPU because it's made with DRAM technology. So DRAM is cheaper than what SRAM is. So SRAM is the technology that we use to make caches. And it has the highest latency. So it takes like hundreds of cycles to access global memory because it is farther away from the processor, right? So the core, it's farther away from the core, so it takes longer to access, as well as the DRAM technology itself that cannot ensure like a one cycle access, because there's some lot of internal states that need to be updated before you can retrieve the data. So the idea is, if it's slow, then how can you use global memory efficiently? So the basic concept, again, revolves around this idea of how memory access transactions are organized. So on the older GPUs, which is on NVIDIA system, it's called, so any generation of GPUs on NVIDIA is identified by a compute capability factor. And so anything less than 2.0 is like the Fermi and old GPUs. So we don't have to worry about that. And the newer GPUs are all based on full warp. So that's all compute capability greater than 2.0. And so that's how memory access transactions are organized. So that's the granularity of memory access transactions. And the accesses are done in 32, 64, and 128 byte segments. And the basic idea is that consecutive addresses can be read quickly. And that's because of how the hardware is organized. So the same, and on the other spectrum, we have that if you have non-sequential accesses, where say you have an array of 100 elements, and a thread would first access x of 0, and then the other thread in the warp would access x of 100. So that would be slow because that's non-sequential access patterns, and so those accesses will be serialized. And when the device driver or the hardware allocates memory, the memory allocations are aligned to 256 bytes, and that's for performance purposes. So for half warp, accesses can be done in as little as one transaction under certain conditions. So this entire concept of how the hardware accesses memory is based around the concept of memory coalescing. So the idea is that you have this memory controller that receives a load request or a store request, whatever it is, from the thread, right? So it looks at the segment containing the address the first active thread is requesting. So for example, if you have 32 threads and they are trying to request, say, different addresses, so the memory controller will look at the segment containing the address that the first active thread is requesting from that warp. And then it will also look for other active threads requesting the same segment, right? For example, if we have 32 threads and they are all accessing the same 64-byte segment or whatever, then the memory controller can identify this. And so what it can do is that instead of sending 32 different transactions, it can coalesce these transactions into fewer transactions. And then it will mark the service threads as inactive. And so the concept of active and inactive threads revolves around this idea that based on predication. So for example, if you have a kernel where you have a if loop and you say that you have a variable inside x, and you say that if x is greater than 2, then do this, and x is less than 2, do this. So you know that in a GPU, the way this will execute is that the hardware is going to execute one of the conditions, and the other threads are going to be inactive for that particular access. And the second time, the other threads are going to be active. So that's what the concept of active versus inactive threads arises from. And so this process is going to be repeated until all the threads have completed their memory accesses. So you can see that why it's good to have coalescing, because then you complete your accesses in shorter time or shorter number of tries. Any questions so far? You can post it in the chat window and you can interrupt me. So here we are just showing a diagram in one transaction, which is a 64-byte segment, and all the threads are trying to access this. And here there are like two separate transactions, 64-byte and 32-byte segments. So think about how a 2D array is actually laid out in memory. So for those of you who know C programming, you know that C follows a row major order, which means that if you have a 2D array and the elements next to each other in the same row are placed consecutively in memory. So for example, here all these 0, 1, 2, 3, etc. will be placed consecutive next to each other. So if I have a warp, which is a group of 32 threads, and they all access consecutive elements within a row, so then that access is fast, right? Because those numbers will be lying within a shorter segment of memory. Whatever the type of data type it is, it will dictate that. But in general, those will be placed closer to each other. On the other hand, if I try to have threads access blocks along the same column, so the way this is, since this is a row major order, the elements belonging to the same column will be placed further apart in memory. So it's hard to get good coalescing because these elements are scattered across the memory. So you can't really coalesce because they don't fit in the same memory segment. So just something to be aware of. Where you want to use like this or have this idea of what is a row major and column major. So in C or in CUDA C, so CUDA is based upon the C extensions. So it follows a row major order, which means that elements in the same row are laid next to each other. And that's why they can be coalesced. And in case you're wondering, this is the same thing that would happen in a CPU program as well, if it's written in C. On the other hand, I don't know if anyone has experience with Fortran, but in Fortran, it follows a column major order. So where elements in the same column would be laid consecutively in memory. So just to summarize the global memory concept, first of all, it has very high latency, 100 cycles per read, and it resides in the RAM memory, so which is the GDDR5 or some advanced technology beyond that. So ideally, if we're accessing global memory, we want to access addresses that fall into the same 32, 64, or 128-byte blocks so that we can coalesce the reads. And again, the main idea, as we have mentioned before, is to have very predictable and ordered access in memory. So we don't want to have scattered accesses which can harm performance. So any questions about the global memory concepts? Okay.
Hi, could you explain warp again?
A warp is a group of 32 threads that execute in a lockstep fashion on a GPU.
Okay.
So yeah, it's like the hardware will execute these threads or try to execute these threads together. So it's a granularity of execution. So we covered this in the previous week's theory class. So if you look at those videos, you'll be able to better grasp it. But the basic idea is that it's like a group of 32 threads that the hardware executes on the core. So now, once we are done with global memory, let us come to registers. So registers are traditionally the fastest memory, and that's because they are made of higher technology. So it means that they are costlier, but they are faster to access. So you can't have a large register file, but you can have a small register file and access it very fast. So what is assigned to registers, right? How do we store things in registers? So in CUDA, it's basically that if you use any variable inside your kernel. So for example, in the previous class, previous lab as well, people have seen this TID variable, which is a thread ID. So that thread ID is a private variable that belongs to a specific thread, and that will be stored to register. So that's how those type of variables would be stored in registers, basically any variable that is private to a thread. So you can also have some arrays which can be declared as registers. So that would only happen if the compiler, so when you use NVCC or some whatever compiler it is, and it thinks that the array is small and it can fit on the register, then it will be allocated on the register. So this is a private register that you declare inside the kernel, and most of the times the array sizes are usually large, that this does not happen that frequently. So if we look here, right, the thread ID, TX ID, TY ID, all these variables would be stored in registers. And some arrays again might be declared registers if their size is very small, and this would happen at compilation time. So the size of the register file is 64K entries, and this is for this generation of GPUs, like the Kepler GPU that we are talking about. I'm not sure, the newer ones might have a larger register file. You can check that. Those specs are usually available publicly. So these registers are private for each thread, and in the Kepler architecture that we're talking about, it supports a maximum of 255 registers per thread. So the way you can find out how much registers your threads are using is doing a command like this, like using NVCC. So this will try to compile your, say we have a file called matrixmul.cu, which is a CUDA application. Then it will print out this information here, which shows use 14 registers. So it means that in this particular application, the kernel, each thread used 14 registers, but there's a maximum of 255. So you can see that there's a lot of free registers that are available. So in case you're wondering what this PTX is, so it's a sort of a pseudo assembly language that is used in NVIDIA CUDA. So normally we don't program in PTX, but people who develop like high performance CUDA libraries, they would use PTX to write their code. So one of the question is, what happens if we exceed the register hardware limit? So you know that each thread has 255 registers, right? That's the maximum that is allocated. So what happens if we exceed that limit? So it will spill to local memory, and this is where a register spill can actually harm performance. So to understand that, we need to know what local memory is, because so far we haven't introduced it, right? But the question is, where is this local memory? So it looks like it's very close, right? Actually, it's not. It's located in the device GDDR memory. So even though the name is local memory, it's actually part of GDDR memory. So you can imagine that hundreds of cycles might be taken to load variables. So this is one of the key reasons you should not use variables, too much inside the kernel. Try to keep them at a minimum. For example, there's no point in storing intermediate computations. You can have like a single statement wherever it's possible. So ideally, you don't want register spills to happen, because you can imagine like if each thread has to load the variables for computation from global memory, it's going to be extremely slow. So this is where the concept of local memory starts, right? So variables that cannot fit on the registers would go to local memory, and that would be basically arrays that cannot be defined in compilation time, or large local arrays, as well as any variable that doesn't fit in the 255 register limit. So the key concept to remember here is that you don't want register spills to happen, because it will be stored in device GDDR memory, which takes hundreds of cycles to access. So the one difference that is important to remember here that identifies, how local memory is different from global memory, because like we have mentioned, global memory is stored in device GDDR5 or the GPU DRAM, as well as local memory. But the key difference to note here is that the local memory reads are cached in the L1. So it's actually cached in the level 1 cache of the GPU. So which means that most of the time, or sometimes, you'll have faster local memory access than you can have global memory access. So that's a hardware spec that says that any reads to local memory will be cached in L1. So that's why they can be faster than global memory reads sometimes if there's a cache hit. Is this concept clear to everyone? Okay, we'll move on. So now we come to another important form of memory, which is shared memory. So again, any form of memory that is on chip would be faster. That's because it has a higher bandwidth. So it's usually made with a technology like SRAM, which is much faster, but at the same time, it's much more expensive than DRAM. So you cannot have a large SRAM because it's too costly to implement. So shared memory is sort of a user programmable cache that's available on GPUs, and we'll see its use cases here. But the basic idea is that it has a much higher bandwidth, lower latency because it's closer to the chip, right? So you don't have to go all the way to main memory. And as usual, like anything that is expensive would be small, so it's much smaller size. And shared memory works at the level of a block. So the key concept to remember here is that all threads that are part of the same block can access the same shared memory access space. So remember the concept, you have a grid, and then this grid can have multiple blocks. So each of these threads that are part of a block can access the same shared memory. And when the block finishes, so all the threads are executed, the shared memory will be released. So if you want to have like this sort of ordering inside the thread block when you are using shared memory, you should use the sync threads to synchronize threads. And this will help to avoid hazards or race conditions. And we'll take a look at what that means in an example later. So in terms of how you can use shared memory, you can declare it in a kernel or in the kernel call, which is a dynamic allocation, and it uses the attribute shared. So for example, here we are declaring this variable as shared, right? So this is an array which will be stored in shared memory. So that's how the compiler identifies that this variable is meant for shared memory. And this is another way to declare it. I mean, it's a matter of choice which one you want to use. But here the important thing to note is that this is a static allocation, whereas this is a dynamic allocation. So the way you would call shared memory, right, if you are using like a dynamic call, is through here. So for example, if you see the static version of the shared memory, you can see that the third argument is empty in the kernel call, but here we need to pass the size of shared memory. So this is a dynamic shared memory version, whereas the above one is a static shared memory version. So if you remember this kernel signature in CUDA, we left this parameter empty. So there's a third parameter there, and that has to be the size of shared memory if you want to declare it in a dynamic way. So it depends on how you want to use. So one question is, what if you need multiple dynamically sized arrays in a single kernel? Anyone has an answer to that? You can post it on chat if you want. So that's the thing, right? You have to declare it as a single extern unsized arrays before, and then you use pointers into it to divide it into multiple arrays. So as you can see, it's quite complex, and it's best like you avoid this kind of array allocations. So don't try to do something like that. I mean, you can do it and you can get it running, but it will be very cumbersome to manage. So ideally, you don't want to do something like that. So any questions in shared memory so far?
Could you explain this dynamic array part once again?
The dynamic shared memory? Yeah, sure.
Yeah.
So the idea is that you can have shared memory in two ways. You can declare it statically in the kernel. So you can declare the size, right? So this is a static allocation where you're defining the size as 64. In a dynamic allocation, you are just declaring the size, but you was just declaring the array, but not really the size of the array, right? Is that clear
Yeah.
first?
Yeah.
Okay. So then the idea is that if you do like a static, if you call the static version of the application, then the kernel call remains the same, right? You do not put any extra parameter here in the kernel signature. But if you have a dynamic reverse, or if you're calling the dynamic version of the kernel, then you declare the size here and into size of int. So this is the size of the shared memory.
Okay.
So yeah, depending on how you want to program, you can use either of these. I'm pretty sure it won't have an impact on the performance of the application. It's more of a programmability thing, how you want to program.
Okay.
May I ask a question regarding
Yes.
the global memory?
Yeah, sure. Go ahead.
What kind of information is being stored in global memory?
So for example, any kind of like data, right? So first of all, say you have any array or something that you are passing in the kernel, right? For example, here we are passing this d of d whatever, right? This is an array. Let's think about that. So that will be stored in global memory by default.
Thank you.
Yeah. So and then the idea is that during execution program or during the execution of the program, those might be cached, may not be cached. That would depend on how the hardware decides, something like that.
Okay, got it.
Yeah.
Thank you.
Yeah. So the good thing with the shared memory is that, as we have seen here, it's a programmable feature. And so one thing to note here is that the shared memory is not actually a separate physical space. So the level 1 cache on the GPU and the shared memory use the same physical space of this memory, right? Of the 64 kilobytes. So this is the size of the L1 cache on the Kepler GPU. And the programmer can configure how much of these they want to have as shared memory, which they want to manage, and how much of these should be available for the hardware in the form of L1 cache. And you can actually do it in the program call like this, right? So for example, here we are setting these parameters. So these are the different options that are supported. So you can't have arbitrary options. So for example, so this is the function call CUDA device set cache config. And these are the different options. So if you do prefer L1, then a 48 kilobytes will be allocated for L1 and 16 for shared. Prefer shared is opposite, right? So 16 kilobyte for L1, 48 kilobyte for shared memory. And prefer equal, both are equal, so both are equally divided. And so how much you want, you should know as a programmer that how much is going to be used by the thread block, and then put there accordingly. If you set this option incorrectly, the problem that will happen is that, say you did the prefer shared, right? And so the hardware reserved 48 kilobytes for your shared memory. In that case, if there's, if you're not using that space, then it's a problem, because then the L1 cache cannot be used for caching like other data. So just be cognizant of this fact when you program for shared memory. So it is a very useful type of memory that is available in GPUs, and it's very helpful in optimizing some algorithms. And I think one of the lab assignments has you use shared memory to do performance improvements on a GPU program. So here is a template of something that uses shared memory. So first we have this shared block of size 1024, and then we are declaring a temp variable. So the first thing that is happening is that, so this is the shared memory variable, right? My block. So we are storing the variable with data of TID, where data of TID is the array you passed. So then we want always, so the one thing to note is that the scope of the shared memory is all threads within the same thread block, right? So we should ensure that all the threads have loaded their values into shared memory. So for example, if I want to read from shared memory, so I want to read something from my block, I need to ensure that all the threads have finished writing to it first, because that's what this part is doing, right? So that's why it's important to synchronize between the threads using sync threads. And then, so this, you can ignore this because this is like application specific. It's calculating some temp variable. But an important thing to notice is that now it's updating my block and then write the result back to global memory. So it's storing the result back to data again. So if I don't place this sync of threads, you can imagine what will happen, right? So anyone has an idea of what will happen if I remove this sync threads? You can speak up, anyone who has an idea. So think about how the threads would be executed and what might happen if I remove these sync threads. So the goal of sync threads is to synchronize between threads of the same block. Anyone with the answer? You can speak up if you want, or can type, whatever. So think about race conditions, just a hint. So what might happen if say say thread number 3 reads before thread number 1 writes to this location, what will happen? Or is it something that can happen first of all? So the key idea is that, if you don't place this sync threads call, what will happen is that some of the threads might have finished writing to shared memory while the other may not have. So the CUDA hardware does not provide any guarantee that thread 1 executes before thread 31, right? So you cannot have any guarantee of ordering between the threads. So if you do not synchronize with this command, you will read garbage data from shared memory. So it's not like your program can crash. It might crash, but in this case, at least what will happen is that you will read wrong data. So because the thread may not have finished writing to this block. So is the concept of synchronization clear to everyone? I'll take that as a yes. So why is shared memory so fast? I mentioned this before because it's made with the advanced technology, which is SRAM. It's much expensive and it's closer to the cores. So, sorry. So the idea is shared memory is closer to the cores, and so it's faster. So let us take a look at how this shared memory is actually organized. And this is actually important to understand how this memory is organized, because if you don't understand this concept, you will not be able to tap into the full potential of this hardware feature. So basically the way the shared memory is organized is in the form of banks. So you can think of each banks as separate chunks. So here we have these separate chunks of shared memory banks. And then we'll talk about the below figures now. So the basic idea is that, so you have these threads read from different banks, right? So this looks like a good case because each thread is reading from a separate bank. So it does not necessarily mean that thread 0 always has to read from bank 0, but this diagram is just to show you that, the left-hand side diagram, each thread is reading from a separate bank. And there are 32 banks in the shared memory, right? And then successive 32-bit words are assigned to successive banks. So for example, bank 0 has the first 32-bit number, bank 1 will have the second 32-bit number, etc. So there are 32 total banks in the shared memory of the Kepler architecture. So remember, like some of these features might be architecture specific. So if you are programming tomorrow for a different GPU, you want to take a look at whether these things have changed or not. So the bandwidth is 32 bits per bank per 2 clock cycles. So that means that for each bank and from each bank, a thread can read a 32-bit value in 2 clock cycles. So you can imagine how fast this is if you compare to global memory or in general device memory on the GPU, which is 100 clock cycles. So the shared memory requests for a warp are not split, right? So that is something to know. And then there's a concept of a conflict on a shared memory, which is very important if you want to optimize performance. but there are no conflict if you access to bytes in the same 32-bit word. And we'll talk about how the conflict scenario looks. So let's take a look at the second figure here, right? So you can see that thread 0 is accessing bank 0, and thread number 3 is also accessing bank 0. So these two accesses will be serialized because the bank cannot service both these threads at the same time. So that's important to know, and that's harmful for performance. And similar here, like thread 5 and thread 15 are accessing the same bank. So that is bad for performance. So just to correct one thing. So in the second figure, you'll actually not have conflicts because it's accessing like the same, if access to the same bytes in the same 32-bit word, there'll be no conflicts. But here you can see that they are accessing at the same time. So this results in a conflict. And what I mean by conflict is that it will cause accesses to be serialized, which can harm performance, because the first thing will happen is that thread 5 will read from bank 7, and then thread 15 will read after that. So these two accesses are serialized. They cannot happen parallelly. So we'll take a look at the diagram a better way so that you can understand this concept much better. So the basic idea is that shared memory is fast, like 2 cycles, unless 2 or more threads in a warp access the same bank. In that case, you have a conflict. So if 2 or more addresses of a memory request are in the same bank, the accesses are serialized. And this concept of a bank conflicts exists only within a warp. So you do not have bank conflicts between 2 warps. There's one exception to this though. So for example, if I have all the threads here, like thread 0 to 16 accessing bank 0, in that case, the hardware has a special feature by which it can actually broadcast this value to all the threads. So we'll see how the broadcast looks like. So basically, if you're trying to read just one value, right? So all the threads now read one value. In that case, there's a special way the hardware handles this, which is called a broadcast. So here's the diagram, right? First of all, the basic case, all threads access different banks, no contention at all. So this is the best case scenario. You have good performance. Now let's take a look at the another case. Now it's a problem, right? So what will happen is that the first, these sets will be allowed to access, and then the other ones will be serialized. So if we take a look at the previous diagram, right? So all of these would happen in parallel. Let's take a look again. See, so all of these would happen, get serviced in parallel. But now with threads conflicting for the same bank, we have this problem, right? So these two accesses will serialize. So previously it would take like 2 cycles. Now it's 4 cycles. So again, now more it gets worse, right? So now you have all 4 different. So you have 4 threads accessing the same bank. You can think of it that way. And now there's more contention. So this is now even takes longer. So as a GPU programmer, when you're programming shared memory, you need to understand this concept of a bank conflict, because if you have this sort of pattern here where so many threads are accessing the same bank, you will run into performance issues. So just to be aware of that. Now the special case that I was talking about, right? So let's take a look again. So all these threads accessing the same piece of memory. So let's say all these 32 threads were accessing bank 0. So then the hardware has a special feature to deal with this. It's called a broadcast. So it will do only one read and then broadcast it to all the other threads. So this is a hardware specific feature. So this is not a problem. This doesn't harm performance because it's a 2 cycle read, right? So there's no issue with that. Anyone has a question on these 3 different scenarios? So in summary, shared memory is very fast. That this can provide 2 cycles per read. The key concept to understand is the concept of banks. So the memory is divided into banks, 32 banks. So the main thing that is important for you to know is that you don't want to access the same bank with different threads in a warp. So any bank conflict will serialize the access. unless of course they all access the same 32-bit address, in which case you can broadcast. So when is shared memory useful, right? So you can think of applications where you are requesting a lot of data from global memory, but if you can cache them in shared memory, then those accesses can be very fast. So you can reduce the 100-cycle latency from global memory. But again, you need to do your programming work for that. It's not something that happens automatically. You need to declare the shared memory, ensure that synchronization is happening correctly between the threads. So this marks the end of shared memory. Any questions about this? Okay. Let's talk about caches again. So first of all, you cannot program the cache. You can program the shared memory, but the caches are handled by hardware. So 4 different types of caches on the GPU. The first is the level 1, which is the closest to the core. Then we have level 2, which is shared between the cores. And then we have 2 special types of caches called read-only constant memory and read-only texture memory. So one L1 per SM, right? So each SM or SMX has one L1 cache, which is private. The L2 is shared between all the different SMs. And then the L1 and L2 would store data for local and global memory, which we mentioned before. So this also includes register spills, because if you remember, register spills go to local memory. So GPUs like Kepler can configure that reads are cached in L1 and L2. So you can actually pass a special flag to the compiler by which you can say that you don't want your data to be cached in L1, right? So in that case, it will just bypass. And there might be situations where you want to do that or not. So that would depend on the application programmer. But you cannot cache store operations. So just be aware of that. Only load are allowed to be cached. So what is constant memory, right? We've been briefly talking about it. So the basic idea of the constant memory is that it's first only read only. So that means that you cannot write to any part of memory that is located in the constant memory. It's not allowed by the programming model itself. So there's a separate cache that is dedicated to constant memory. And the way you declare it is on a global scope outside of the kernel. So one important thing to note is that it's a limited resource. So I think it for all generations of GPUs is 64 kilobyte size. There's a size of the constant memory. And to use constant memory, you would use the attribute, underscore constant. So one important thing to note is that for constant memory, the host has to initialize it. So using this API. So CUDA memcopy to symbol, and that is the symbol that is associated with the constant memory. So this is where you declare the variable. You use the signature const, and of course this is source, and for example, which host source you are copying the data to, and then the count. So this has to be done for constant memory based allocations. So when is it useful? It performs better when all the threads in a warp would access the same memory address. But you should not use it if all the threads in a warp access different memory address and is only accessed once, because that is harmful for performance. And the other thing is that the variables that you use in constant memory don't have to be declared in the kernel invocation. For example, when you invoke the kernel, you pass a set of variables to it. So the constant memory residing variables do not have to be declared in that. For example, here we are showing that how you can. So you have declared this variable as a global constant m, and then we are doing this memcopy to symbol. So copying this variable m to the device, and this is the kernel when we are using this m value here. So you can see that in the kernel function call, we are not really passing m, so it doesn't have to be passed. So one of the things important is that when you declare something as constant memory, the uses is only read only. So again, you cannot write to constant memory. I have not tried it, but I think the program will crash or it will give you some incorrect results. So reading from constant memory can conserve memory bandwidth when compared to reading the same data from global memory. Anyone has any idea why that is the case? So here are the two reasons. The first is that a single read from constant memory, it can be broadcasted to all the other threads. So that effectively saves up to 15 reads, right? So in a half warp scenario. And the other thing is that the constant memory is cached. So you don't have to go all the way to device memory for consecutive reads to the same address, because there's a special cache that stores constant memory data. And now coming to the last type of memory, right? So we have covered shared, registers, local, global, and constant. So the next type is texture memory. So this also resides in the device memory, so the same GPU DRAM. And there's a special texture cache, which caches this information from texture data in a per SM fashion. So every SM has a texture cache. So the scope of this texture memory is global memory. But the thing is that there's a special way to access it, and that is only through a dedicated read-only cache, which is called as a texture cache. So when do you use texture memory? I think like if you work on any image processing application, so when your data has like 2D spatial locality or 3-dimensional spatial locality, that's when using texture memory can be helpful. So example of how this works, right? So you have this image data, and let's say your algorithm is such that you would read like these yellow colored elements 0, 4, 8, 12. So you can see that these are not coalesced in a regular 1-dimensional memory, right? Because they are far apart in memory locations. So when a cache miss happens, you need to load new data from this slow source. But if you declare these in texture memory, right? So the way since this is a special kind of memory, you can actually service this pretty fast from the texture cache. And you can, I think like the image processing lab that we have on deals with texture memory. So you can get more experience there on how texture memory in generally is used and what are the advantages of it. But in general, like as I mentioned before, if you are using any sort of image-based data, you would definitely want to take a look at texture memory because it can be really helpful. So how to use texture memory? There's just like a constant memory, there's a way to reference texture memory as well. So yeah, so here we are declaring this texture variable and declaring it to be read mode element type as a variable text. You can see that there's this is a kernel that uses this. So first thing is that you have a buffer, right? So this is a call kernel function, and then you need to bind the texture to a buffer. So that's using CUDA bind texture. So this is a special API that is used to bind a buffer to a particular texture. And then once you do that, you need to call the kernel. So in the kernel, you can use the texture memory in however you want. So if this example looks complicated for now, that's fine, because we're not really concerned with using texture memory right now. But we'll explain it in more detail. I think it's in the image processing section. But the key takeaway I want you to take away from here is that if you think about working with imaging data, then texture memory is the type of memory that you should be looking at. And but using it is more complex than what is shown here. And there are some nuances that you need to take care of. So just to summarize the memory model, so each thread can read and write on the per thread registers. So it can read and write to per thread local memory, like we saw. It can read and write to both per block shared memory, and then it can read and write for the entire grid to global memory, right? So any variable that is declared with as part of global memory can be read and written to. but only in the case of constant memory, the threads can only read, they cannot write. So there are some particular qualifiers that you need to understand here, so that that we mentioned in this table here. So it's important to know these qualifiers because they talk about the scope and what is the lifetime of each variable. So let's take a look at this one by one. So the first is a variable int local var. So as I mentioned, so these are all variables which are, so this one is declared inside the kernel, right? Int local var, so you'd be declaring this inside the kernel. So you already know that this will be stored in register, and this is a private variable for each thread. So the scope is a thread, and this variable will be removed when the thread finishes. So the register will be freed, and that's why the lifetime is a thread. Now we come to another, say, array that is declared inside the kernel. So it's a local array of size 10. So now you know that, say, the hardware, in some cases, the hardware might actually decide to store this in register. But let's take the normal case where this would be stored in local memory. So the scope of this, so this will be stored in local memory. And then the scope of this local array is the thread, and the lifetime is also the thread. So this is important to know because there are two things, right? So this particular local array has the same scope as this local var. The only difference is the memory where it will be stored. So while this integer variable will be stored in register, there's a high probability that this local array will be stored in local memory. So traditionally access to it will be slower. Then we come to this special variable, which is shared, right? So the shared memory, and this is the variable. And when we declare something like __ device, it means that the scope of the variable is, we can declare it as a global variable as well. So the scope of this, so this particular qualifier shared means that the data will be stored in shared memory. So as I mentioned before, each thread in a block can access this shared memory. So the scope would be the shared block itself, like all the threads in a block. And then this shared memory will be released when the block terminates. So that means the lifetime of this variable is the lifetime of the block. So once all the threads in the block finish, the hardware will release this shared memory to be used by the next block or whatever. Then we have, say we want to declare a global variable. We will use the qualifier device. So this variable will be stored in global memory. The scope is the entire grid, right? So that's the scope of this variable. And the lifetime of this variable is the entire application. So this variable will be released only when your entire application finishes. And similarly, when we are declaring a constant variable, this variable will be stored in memory, which is constant memory. The scope is the grid, and the lifetime is the entire application. So just something to be aware of, the different type of variables that you will encounter when programming in CUDA. So something to mention here, automatic variables without any qualifier would reside in a register, except of course the arrays. For example, this one would reside in local memory, or if there's not enough registers, then it will be stored in local memory. So any question about the qualifiers?
I do have a question. It's not regarding qualifiers, but regarding the global and constant memory. So
Yeah.
it basically looks like all streaming multiprocessors can have access to global memory and constant memory. So it's common for all SMs.
The constant memory would reside in the same GPU DRAM as the global memory, right? But the thing is that the constant memory is only read only, so you cannot write to any variable in the constant memory.
Okay, but
So
I mean,
yeah, go ahead. Sorry.
Different threads running on different blocks can still access it, right?
Yeah. Constant memory can be accessed.
Okay.
Yeah.
Thank you.
Yeah. But the main difference with constant memory is that it's only read only, so you cannot write to any variable that you declare as constant.
Yeah, I understand.
Yeah.
Understand that. Thank you.
Yeah. Okay. Any other questions about the memory scoping?
Since arrays are stored in local memory, they take I guess, the longest time to use. So do you like go out of your way to try to not use local arrays?
So local memory is, so if you use local array, it will be stored in local memory, but local memory reads are cached, right? So sort of you can, if you want to use, you can,
Right.
but yeah, I mean, traditionally, yeah, ideally you would want to fit everything in the registers, but sometimes it's just not possible. So in that case, like that would depend on the application and whether how big your array is. But yeah, I mean, since it's cached in local, the L1 cache, right? So it should be fine.
Oh, okay.
Yeah. So, but yeah, if you want to have the best performance, then you want things to be in registers, because that's the fastest access that you can have. Is that clear?
Yeah, that answers it. The L1 cache makes it, faster. Obviously, I was on my notes. I just have saying it's hundreds of cycles to access, so that was my concern.
Oh yeah,
You
yeah,
cleared that up. Thank you.
yeah. Okay. So some other notes, scalar variables, which is something like the int TID that you saw in your kernels previously, they all reside in on-chip registers. Shared variables reside in on-chip memory, which is a shared memory. Local variables reside in off-chip memory. So that is slow, but the thing is that since they can be cached, sometimes you can get away with faster performance, but they can reside in off-chip memory by default. And then constants reside in cached off-chip memory. So the constant memory has a separate cache, and then there's of course it also resides in a device memory as well. So just keep these things in mind. So now we come to the concept of synchronization, which is very important in a parallel program. So the basic idea is that you have these two threads that are trying to write to the same piece of data, right? And so you need to ensure some form of ordering between them. And you have, say, another thread that is reading the same data. So you want to ensure have some mechanism in it to synchronize between these two threads, so that you don't end up reading the wrong value later on. Or for example, you are, say, updating like a very you have a particular element in an array, and that same element is updated by multiple threads. So you don't want a situation where this particular element, say, has a value of 1, and then after 10 threads update it, you end up with a value of 2, because that would be wrong. And this can happen if there's no guarantee of ordering. So for example, I'll give you a good example of that. So say, like, all these 10 threads read this value, and then all of them write at the same time, right? So they each have their private copy of this variable, and they write. So they increment it by 1, right? So if there is no way to ensure synchronization, then the final result that you'll end up is just 2 instead of 10 or 11, whatever it was. So that is incorrect, and we need some ways to ensure that this does not happen. So there must be some form of I can say sequencing or operation sequencing that must be ordered, so that you can achieve the correct result. So the question is, how can we avoid this on a GPU? So to do that, we need to understand the concept of atomic instructions. So there's a very special set of hardware instructions. So these are part of the instruction set architecture. So they perform an operation on one or memory locations atomically. So what it means is that when you use these atomic calls, the hardware will provide a guarantee that the updates to that particular location will be correct as would be if they were done in a serial fashion. So the basic idea of atomic operation is that it's indivisible or uninterpretable. And the basic definition of atomic operation is either succeeds or fails, regardless of what instructions are executed by other threads. So the atomic instructions are what we are going to use if we want to update, say, like a global counter, something like that. So what are the common use of atomic operations? So first, in collaboration scenarios, right, on, say, you have an image histogram, and you have let's just say you have an array of 100 elements, and you want to count how many of these values are tens, how many values are 2. So your output array will have something like, there were 50 elements that are 10, there were 10 elements that are 2, something like that. So if you think about the way this program will be written, you can say that the location 10 will be updated by multiple threads, because each time a thread sees the value of 10, it is going to update that value. And this is what a histogram is, right? So those of you who know what a histogram is, that's what the basic concept is, right? You're trying to find out, or basically trying to bin things together. So this is when atomic operations are important. So when you say want to update that counter or location, if you use an atomic instruction to do that, the hardware guarantees that those operations are uninterruptible or indivisible, and that you will see the correct result eventually. So some of the important things or places where you'd use atomics are counters, locks, and flags. And then CUDA as a language provides atomic functions on both shared memory and global memory variables. So these are the atomic operations that are provided. You can take a look online at what, I'm not going to go into details, but these are different ones. For example, an atomic add is going to be used. Say you have a counter and each thread increments that counter for something like a histogram or something like that. So then you would use an atomic add, and that would basically ensure that any increments to that variable are atomic and then are seen in the correct order. And similarly, you have sub, max, min. So these are different type of atomics that can be used. And there are other bitwise functions as well, like atomic and atomic or. So what you use is going to depend on the application at hand. So for example, here we have atomic add int. So this is the variable that we want to update atomically. And then we have a counter variable, which can be 1 or 2 or anything, right? So this would ensure that this variable is always updated atomically, and there's no situation where a race condition happens. Are atomic functions, like the basic concepts, clear to everyone? Okay. So the second line basically shows you how it looks in the PTX, which is like a pseudo assembly language of CUDA. So on Kepler hardware, that's how these atomic instructions get broken down into assembly. And then in Maxwell, which is a newer generation, I think Maxwell is the generation after Kepler GPU. So that's how the atomic instruction would look like. So in some hardware, it's like you have to synchronize, but the newer hardware, everything, there's a native atomic instructions which are provided for you to make programming life easier. So atomic conflict degree is like there's within a warp, there's a conflict degree from 1 to 32. That's because if each of these threads try to update the same counter, then you'll have a conflict because but although the hardware manages it for you, but of course it's detrimental to performance because those operations are serialized in hardware, the updates. So you can see here, right? So this particular 2 threads are writing to the same variable, so it's an atomic conflict. So those will be serialized. On the other hand, here on the left hand side, both of these threads are updating different locations in memory. So that's fine because there's no atomic conflict. So many applications in GPU would require you to think about synchronization at different levels. The first is synchronization within a block, which is called intra-block. So synchronization between threads that are part of the same block. Then we have synchronization between threads that are different blocks. And then finally, we have synchronization between the CPU and GPU. So how can we achieve these different forms of synchronization? So with intra-block, that is already seen that with shared memory. So if all the threads are part of the same block, we can use sync threads to ensure that our threads within the same block are synchronized. So this hardware instruction guarantees you that all threads in the block, that is after, or the entire code after sync threads, will be executed only after all the threads have reached that point. And we also have atomic operations in shared memory as well. So these are the 2 ways to synchronize between threads in a block. So note that we mentioned specifically in shared memory, because atomic operations can happen in global memory as well, and then it's not really intra-block. So now how do you synchronize between two different blocks? So there's actually no explicit way of doing this. The only way to do it is to terminate kernel and synchronization point, and then launch new kernel to continue after. So I think the newer generation of CUDA hardware, which is I believe the Ampere and Volta GPUs, they have some sort of primitives that are related to inter-block synchronization. Don't take my word for it. I'm not really 100% sure, but I know they introduced some new primitives for synchronization. And I think those do allow for inter-block. But at least for the Kepler generation of hardware, inter-block generation, synchronization is not really supported. And the other thing is that you want to avoid atomic operations in global memory, right? Because global memory is already slow, and then you can think about now updating a very slow form of memory. So that's paying like twice the penalty, because all these updates in global memory will now be serialized. So first of all, it's global memory, which is already slow, and then it's atomic operation, which the hardware will do this sort of serialized access to and update to that. So it is going to be extremely slow, and is something that should be avoided. So when you're programming and you need to have atomic updates, try to see if you can avoid using global memory. Maybe use shared memory if it's possible. But again, that requires you to think about the program differently. So there's a trade-off between how much time you are willing to spend to write a good program versus how much performance you'll gain. So that's like always a trade-off. So something to keep in mind. And then finally, we have CPU GPU concurrent execution, and there's only one way to do that is to you've seen the API CUDA device synchronize. So that actually ensures that that the GPU kernel has executed before the next statement continues. And also any form of CUDA memcopy is synchronous unless you use the asynchronous APIs. So those are synchronized means of synchronizing between the CPU and GPU. So yeah, I mean, that's it for today's class. Any questions? I see 2 questions here. Let's see. Okay, not really questions, but anyone has any question? Before everyone leaves, did everyone have? I know one person, Gaurav, doesn't have his account on Discovery, and I've contacted the Discovery people to make his account. Does anyone else not have their accounts yet on Discovery cluster? You can just say here, and we can ensure that we get you the account fast. And if you have any questions later on, you can always post them on Piazza. I know Gaurav, you wanted to speak, so you can stay online, or you can ask your question now as well if you want.
I just want to ask, like, what should I prepare for tomorrow? Like, what are we going to do tomorrow?
For tomorrow's lab, you mean?
Yeah.
So I mean, if you get the Discovery account, I don't know if they have it yet. They will. I can see the status. I don't think it's done yet. So, but if you get it before the class starts, you can try out the first labs. Have you used the Discovery cluster or any form of cluster before?
No.
Then yeah, you should definitely look at the lab.
Like, I have experience on Linux and Unix.
Okay, yeah, that's good. That should be good. So you should take a look at the first lab slides, right? The lab one has a slide or PDF, whatever that is, and then try to understand like how the Discovery cluster works in general.